or if you ever have any other questions or specific questions, be sure to take down my email or website and just reach out and say, hey, Lynn, I'm stuck on these problems. Can you help me through? And just take a screenshot of whatever it is and just shoot me an email. And I will write you a step-by-step response and send you a picture back of how to approach it. And if you want additional problem sets that are similar to it because it's a tough problem, I'm happy to do that. And that's for anything that we've done or anything that you encounter. And hypothetically, if you don't choose the SAT and you choose the ACT, there are other advanced problem sets that are going to come up there that I think will be really useful as well, that we could potentially go through that we have not covered here, specifically for SAT. So for the SAT math review today, we're going to look at shapes. We're going to look at complex formulas. We're going to look at advanced problem sets. So what does that mean? Well, we're going to start with the formulas that are given to you on the SAT. And we're actually going to do quite a few problems where it's like organizing lots about triangles, length of an arc and area of a sector related to a circle, and any sort of 3D shapes, and also breaking down shapes. So we'll take a look at that. So again, these are the formulas that are given to you. This also leads me into the formulas that are not given to you, which we spoke about before. Just going to make that a little bit bigger. So we've already covered, just as a review, everything about slope, everything about standard form of a linear equation, everything about functions thus far. We've done a lot with percent change. We've done quite a bit with exponential growth. But it's the guts of this page here that we are going to cover today. And so that's starting from equation of the circle, which is x minus h quantity squared plus y minus k quantity squared equals radius squared, where h comma k is the center of your circle. The square root of r squared would determine your radius of that circle. So we're going to do some circle problems and completing the square. I'm also going to approach length of an arc and area of a sector, so pieces of a circumference and area of that sector, that piece of the pizza. We're also going to look at SOHCAHTOA, sine, cosine, and tangent, and remembering your fractions. So I always write them this way, and actually a student a couple years ago, because I always wrote it out the traditional way, SOH space CAH space TOA, but she was like, why don't we write it as a fraction? And then it reminds you of what to do, like opposite over hypotenuse, like you actually get to see it. I'm like, oh my gosh, that's brilliant. Can I steal that and use it? So I've been using this for a few years and I like that better. It's a great idea, great innovation. But it helps you remember opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. So we'll talk about that. We'll also look at 30, 60, 90s, and 45, 45, 90s, how they relate to a bigger shape. And finally, whoops, click on the wrong side there. We'll look at unit circle and the basics of unit circle. So let's jump right into it. We're going to talk about length of an arc and area of a sector. What I'm going to do is use my Twidla page over here, cover over the problems as I've done in the weeks past. And what I'm going to do is just go through a couple of the problems here. What I've already done, wisely Snow, I already actually put all the answers below. So I'm going to send the updated PowerPoint to Peggy later, in addition to the recorded conversation that we have today. So then that way, if you've already done some of these problems as a preview and we want to double check our answers or you want to go back to these later, you have them. Okay. All right. So we're going to jump into the first one here. And what I'm going to do is just move this over, make it a little bit bigger so we can see and cover over some of these other problems. Okay, so length of an arc, an area of a sector. So what we're going to do is just talk about a circle in general. And when you have a piece of the pie, okay, that is area of the sector. So area of the sector. Well, this is the first time I'm writing today. Not that I'm like taking a lot of time off of writing, but it's always funny like to see how poor my handwriting is first thing. Okay, so area of the sector, x over 360 times pi r squared. So what it's saying is that the degree that's given out of 360 times area formula. And then if we're talking about length of the arc, that's the piece of the crust of the pizza. That's a piece of the circumference. So this is going to be, I'm just going to write it in a color we can read. This is what they call length of an arc. So arc stands for circumference. So it works the same way. It's going to be a degree out of 360. So it's a part of the total circle times circumference formula times 2 pi r. So that's how they're going to calculate this, whether it's going to be a piece of the crust or if it's going to be a piece of the crust or an actual slice of the pizza. Okay, so here, actually, this is kind of funny because this is a radians problem. It's also 30, 60, 90, but it's also talking about a circumference. So this is actually going to be sort of the unique problem that pulls all of our concepts together, like of these big concepts today. So we're going to start with that and actually unpack it too. All right, so here we have our circle, and they're talking about this point here, which is root 3, comma 1, and this is O, and then this is A, and then this is B here, okay? And this is obviously the x-axis and the y-axis. And so they say in the xy plane above, O is the center of the circle, and the measure of AOB, so this angle here, AOB, is pi over A radians. So if you know anything about unit circle, when they're talking about the length of that arc, pi over A radians, what is the value of A? Okay, so what we can actually do here inside of this lovely unit circle is to actually create a triangle. And you'll notice that the x is root 3, and you'll notice that the y is 1. Okay, well, think about that. If we go back 2 pages to our formulas here, and we're looking at 30, 60, 90, notice your root 3, notice your 1. Okay, so if we're taking a look at these problems here, so root 3 and 1, that's a 30, 60, 90. Okay, so let me just draw 30, 60, 90 over here. So if we have 30, 60, 90. So this is actually leading into our whole concept of unit circle as well. To determine unit circle, to convert from degrees, as what's listed right now, to radians, which is based on a piece of the circumference. This is why I present length of the arc up here. The way to convert from degrees to radians is to put your degree measure over 180. I know that's not over 360. We can do that over 360, but then you have to use 2 pi instead of pi, which is fine, which is what's given in unit circle. So it would be 30 over 180, which reduces to 1/6, and then you just put pi in the numerator, and you've converted from degrees to radians, or piece of a circumference. I can do it this way as well. So we can have 30 over 360, which is to 2 pi over some number, and then we'd have to cross multiply and solve and reduce it, which would take us to this place anyway. So what unit circle likes to do is to convert from degrees to radians. So what is the value of A? So A is going to be 6. Okay, so it's using this concept of length of the arc and area of the sector, but then also applying it to unit circle. All right, so let's talk about straight length of the arc and area of the sector problems. That's what a number of these are about. And then if they layer into unit circle, we'll start to get there. Okay, all right, so we're gonna look at 24 next. All right, so 24, so here we have a circle. I actually know that I can draw a shape using what they have, haha. So a little cheater there. Okay, so here, this is D. Okay, here is B, and over here is A, and I'm gonna do my best to connect this in a straight-ish line, okay? All right, and so going from A to B, they say is the diameter. Yep, goes straight through the center. If the length of ADB, so going this direction around the circle, is 8 pi, everyone should be feeling, oh wow, that's half the circle, good. And then the other half is the other 8 pi, which means the circumference of this entire circle is 16 pi. and circumference of the circle is 2 pi r, right? That's the formula. So 16 pi would be equal to the formula for the whole. All right, now it says, what is the length of the radius of the circle? Well, I can just divide by 2 pi and actually solve, because radius would be 8. Now we know our diameter, so the diameter of the circle would be double that, it would be 16. Because circumference, you can either know this is 2 pi r, or pi times diameter also yields circumference. So if we knew that diameter was 16, then we can also make the inference that radius is 8. Okay, looking at number 36, one below it here. Okay, so here's another circle for us. Okay, so here we're going from the length of A to B. Okay, so here we have A, here we have B, X is our degree measure, and they say right here that it has a radius of 10. Okay, so we're going to put that in. And then they also say if the length of A to B is between 5 and 6. Okay, so it's greater than 5 and less than 6. Let's say it's 5.5, okay? And what is one possible integer value of x? So like, what's a degree measure? So if we remember back our formula for length of the arc, because they want to know they already know what is the length of the arc. It's between 5 and 6. So we're picking 5.5 for ourselves. What is one possible degree measure? Remember, that's degrees out of 360 times 2 pi r, right? That's our formula for length of the arc. So I don't know what x is. That's what I'm trying to solve for. But I do know that my radius is 10, and 10 times 2 would be 20 pi. And then that length of the arc is equal to 5.5. Now, mind you, this is question number 36 out of 38. This is a harder question, and also in the math with the calculator. So we can take out our calculators now. So we can solve this as a proportion, which I think would be the easiest. And so we're going to move our 20 pi over to the other side, divide 5.5 by 20 pi. And then what we're going to do is just cross multiply and divide. Now, mind you, your degree measure won't be an integer. It'll probably be a decimal. So my recommendation to you is to round up or round down when you calculate this. So 5.5 times 360 is 1,980. And then if you divide that by 20 pi, don't forget to put the parentheses around your 20 and pi together, because that's a multiplication that's happening together. I'm going to wind up at 31.51267873. Now we can't put that in the answers because, one, they said give me an integer, so you need a whole number. And two, there's only 4 places in the open-endeds for math anyway, so you would just round to your nearest whole number. So I'm going to say 31. And by the way, because the range is between 5 and 6, any answer from 28 to 34, 28, 29, 30, 31, 32, 33, and 34 are all acceptable answers. If I had hypothetically used like 5.1 or 5.2 or all the way up to 5.8 or 5.9, you can see what happens to the angle measure. So this is a really good example, 36, of a length of the arc problem. Here's another 36. So we're going to see another example here of a question labeled 36. You can see where these kinds of problems are popping up in the test. They're a harder problem. They're using this concept that it's a piece of the circumference or a piece of the area. Okay, this next one's going to use some language that we should define, which I think is really important. Okay, so I'm going to make my circle here. And then I'm going to do my best to draw these lines out here, and then draw into the center, and then we'll label. Okay, so this is 60 degrees out here. Here we have M, L, N, O. Okay, so in the figure above, point O is in the center of the circle. Lines LM and LN are tangent. That's an important word. Tangent means it touches the circle at one point and forms a 90-degree angle to the center. You should probably define that someplace. So tangent means that it touches at one point and it forms a 90-degree angle to the center. Okay, so that point of tangency is actually already a massive hint to us about angle measure. Then they tell you that the circumference of the circle is 96. So we don't have to calculate that ourselves. Circumference is already 96. And they would like to know, what is the length of the arc from L to N? Okay, well, that means I need to find out what is the angle measure here, because remember, it's degrees out of 360 times 2 pi r, which we already have. So it would be whatever the degree is out of 360 times 96. Now, here's a really important rule that we need to know about shapes. Any four-sided shape has 360 degrees inside of it. Think of a square. That's 4 90s. 4 times 90, well, 4 times 9 is 36. Add a 0, 360. So any four-sided shape, L to M, M to N, N to O, O to L, this is a four-sided shape. So if I have 360 minus 90, minus 90, minus 60, I'm left with 120 degrees in here. So that means 120 out of 360, which is 1/3 of 96, would give me the length of that arc, which is 32. And by the way, here's a quick geometry hack that if you're left with like a weird sided shape, let's say pentagon or hexagon or septagon or octagon or nonagon, blah, 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 right? If you're trying to figure out the number of degrees inside of a shape, it is the number of sides minus 2 times 180. That tells you the number of degrees in any shape. So if it's a triangle, 3 sides, 3 minus 2 is 1. 1 times 180, 180. Four-sided shape, square, rectangle, trapezoid, parallelogram. 4 minus 2 is 2. 2 times 180, 360. Now, if you want to find, and if they mentioned that the shape is regular, if they say that it is a regular hexagon, regular means that all sides are equal, all angles are equal. So what you do is take this formula, number of sides minus 2 times 180, and divide by the number of sides, and that'll give you your equal interior angle measure. So for example, if I have a pentagon, 5-sided shape, 5 minus 2 is 3, 3 times 180 is 540. If you divide that by 5, the inside angle of a pentagon, all of them would be 108 degrees if they are regular, like if they are equal. So it's a nice little life hack if you remember that from geometry. Any questions so far? Throw them in the chat. Take yourself off of mute. Just let me know. Okay, I'm going to slide over here to number 20. Oops. If I can actually get it to click. There we go. Okay, so here's another length of the arc problem. All right. So you'll notice that they drew a triangle inside our circle. So BC is 2/5 of the circumference of the circle. What is the value of X? Well, X is a degree. And without me doing a whole lot of math, by the way, this is the hardest problem in this set. It's an open-ended 20 math, no calculator. I would do 2/5 of how many degrees in a circle, which is 360. And so 2 times 360 is 720. And then you just divide that number by 5. Notice that I'm doing long division because this is math, no calculator, so I'm not picking up my calculator here. So I'm left with 22. 5 goes into 22 4 times, minus 20, bring my 2 down, and 5 goes into 24 times. So the angle of X would equal 144. So you can use length of an arc in a few different ways. So you can use it from the degree, you can use it from the side length. There's, a few different things. Okay. That's going to take us into another side of circles. So circles, yes, we could do length of the arc, area of the sector. We can also lead into unit circle, which we'll talk about later. But we also have circles, equations of circles, and completing the square. So let's talk about the equation of the circle. And then what we're going to do is work into completing the square. So equation of the circle looks like this: x minus h quantity squared plus y minus k quantity squared equals radius squared. Okay, so h comma k is the center of your circle, and the square root of r squared is your radius. Cool? So what we're going to do is actually learn how to get it into this form when it's in this yucky form to start. So if I have x squared plus y squared plus 4x minus 2y equals -1, the best thing to do is to put your x's together and leave some room. I always joke that it's like sorority and fraternities because x's and y's and letters, and you're going to put them together and leave room for a third roommate. So you're living in a triple in a college dorm. Okay, so x squared plus 4x, they're going to go, and we're going to leave room for our third term here. And then I have y squared minus 2y. Again, I'm going to leave room for the third term here, is equal to -1. Okay, and so the way to complete the square is you take the middle term, which is called the b, and you divide it by 2, and then you square it, and that gets you your third term, which is called the c. Because if you know your standard form of a function, it's ax squared plus bx plus c. So that's the idea. Okay, so we take our middle term, which is 4, we divide it by 2, which is 2, and then square it, which is 4. And the whole rule of thumb when you're completing the square is whatever you do to one side, you have to do the other side. They call that balancing the equation. So I added 4 here, I added 4 here. -2 divided by 2 is -1. -1 squared is 1, plus 1, plus 1. So x plus 2, quantity squared, plus y minus 1, quantity squared, equals 4. So the center of my circle is opposite sides of what's in the factors. So it'd be 2, 1, and my radius would be the square root of this number, which is 2. So that's the way to complete the square. So sorry. Hang on one second. Sorry, our dog is at the emergency room. So I have to send these forms. My husband is over there with him. Oops, definitely don't want to send that there. Okay, hang on. There we go. Okay, cool. Sorry about that. All right, so with number 9, this is more of a visual of where we are taking a look at the circle and its coordinates. So for example, we have x minus 6 quantity squared plus y plus 5 quantity squared equals 16. So 6 comma -5 would be the center of our circle, and our radius would be 4. You know what? I have a trick here. Hang on, forget about drawing that. We're going to do this. So, okay. So here, what we're going to do, boom, 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 boom. I'm going to make the axes look a little funny here because it's 6, -5. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay, so this is the center of our circle right here. Let me just get rid of the graph paper because then I can actually draw on it normally. There we go. Okay, so let's say 6, -5 is like right here. Okay, 6, -5. And then we're going to go radius of 4. So if we go right, they're telling us that one of the coordinates is 10, -5. So that would be over here, 10, -5, which makes sense because it's 4 apart, right? Radius of 4. So the other end of the circle, the question says point P is on the circle and has coordinates 10, -5. Okay, so that's point P over here. And if PQ is the diameter of the circle, what are the points for Q? So if I went over here, here's Q, right? If I go this direction, I would just subtract 4 from 6. So that point is going to be 2, -5. So there we go. So that would be another example. Good chat. Question. Okay, there we go. Oh, thanks. Yeah, it's been a time. This quarantine thing, between schools closing, SATs getting canceled, ACTs having backup dates, then we find that our dog actually has cancer in his foot and has to have surgery tomorrow. So he's doing all his pre-op today. So it's been never a dull moment on a Thursday. That is for darn sure. It's always funny right before I see you guys, and it's always a joy to be with you, but it's always these crazy days that something by the end of the week always happens ultimately. But I know my big guy's gonna be A-okay. So they're really, really talented doctors that we're working with. So I'm really excited. Okay, so we're gonna try this again with completing the square here. So we have y squared plus 16y equals -20. And what we're going to do is, again, we're going to complete the square to get to our equation of the circle. So these are the more complicated kinds of problems that we're going to see on the SAT. People look at it and they're like, that's a weird function. But you have to remember, you have to get it into that equation of the circle form. So, okay, so here we take our middle term, divide it by 2. So 20 divided by 2 is 10, and then square it. So 10 squared is 100. And whatever we add to one side, we add to the other side. 16 divided by 2 is 8, and 8 squared is 64, and whatever we add to one side, to the other side. So this would break down to x plus 10 quantity squared. If you guys need this interim step where you're factoring this into the double factors, by all means, take that extra step. I meant to mention that before, but that's one way that a lot of my students who are have a little trouble with the factoring from Algebra 2, take that extra step in between. And then here, y plus 8 quantity squared, because y plus 8 times y plus 8 would yield that, right? And then 100 plus 64, 164, minus 20 is 144. So the center of our circle is -10, -8, and our radius would be 12. Let's look what they're looking for. What are the coordinates of the center? B. Okay, so that's completing the square. So with number 27, this is going to be the most complicated completing the square I'm going to give you. So it's a little bit tougher. Oops. Here we go. I'm going to clear this out so we have enough room. Okay, so here's what's going to be annoying with this particular problem. We have 2x squared minus 6x plus 2y squared plus 2y equals 45. And maybe everyone is sensing here, oh gosh, there are numbers in front of the x squared and y squared. And you're right, there are numbers in front of them. We need to get rid of them. It's really annoying to have those numbers. You want to complete the square when the numbers in front of your x squared and y squared are totally clear. So what I'm going to do is divide everything by 2. Now you'll also notice that this is number 27, math calculator, hard problem. You get to use a calculator though, which is really nice. So if we divide everything by 2, now we're clear. Now we're clear to move. So that's a really important step that we must take here. And personally, I like dealing with decimals better than fractions when we're working with this kind of problem. So that's how I'm going to write everything, is with a decimal. Okay, so -3 divided by 2, 3 divided by 2 is 1.5. 1.5 squared is 2.25. And whenever I add to one side, I'm going to add to the other. So that's 2.25. And then 1 divided by 2 is 1/2. 1/2 squared is 0.25. And again, we add that to both sides. And then you would break this down. And again, it may be easier just to break down 2.25 and see, like, take the square root of it, right? So the square root of 2.25 is 1.5, if you remember. So it'd be x minus 1.5 quantity squared, because it's going to be the same factor that yields this, plus y plus 0.5 quantity squared. And then we're going to add these terms together. So 22.5 plus 2.25 plus 0.25 adds up to 25. So the center of your circle is going to be 1.5 comma negative 0.5, and my radius is going to be 5. So radius is 5. So that's a tougher concept there, completing the square. Okay. So we're gonna leave circles for a moment. You can see where we're going. Eventually, we're gonna come back to unit circle and more advanced shapes and putting some things together. But what I'd like to do is actually talk about some of the other odds and ends that we come across, which are radical equations and exponent rules. And you know that radical equations and exponents sort of live together. If you have a fractional exponent, that's actually telling you that you have a square root. So let me just talk about some of the basics here. If I have x squared plus x squared, that's 2x squared. If I have x squared plus x cubed, that's actually just the same equation because you can't combine them because you have different exponents. If I have 4x to the 5th times 4x squared, you're going to multiply the whole number terms normally, but multiplication actually is indicating that you should add your exponents together. If I had 4x to the 5th quantity squared, again, I'm going to raise my whole number term to that power, so I would get 16. But now I'm going to multiply my exponents. I'm going to raise the power by multiplying it, so it'd be x to the 10th. If I had 4 to the 1/2, that's the same thing as the square root of 4, which is 2. If I had 4 to the 2/3, let's say, that would be the cube root of 4 squared. Now all of a sudden we're getting a little more complicated. So you'd have the cube root of 16. You can take some values out of that, because 2 times 2 is 4, 4 times 2 is 8, and 8 times 2 is 16. So what you could wind up with is 2 cube root 2, because there would still be a 2 inside. So it goes from not feeling so bad to all of a sudden, whoa, you know, these fractional exponents can get a little complicated. So we're gonna work through some of these things, and including radical equations, because I think if we can sort of flip between the two, it makes it a little easier. Okay, so let's take a look at number 20 here. So I have a equals 5 root 2, and 2a equals the square root of 2x. By the way, this is 20 math, open-ended, hardest problem in the section. So right away, I notice I have a value for a. And so can't I substitute this in for a for the other part of the equation? So I'd have 2 times 5 root 2 equals the square root of 2x, which is 10 root 2 equals the square root of 2x. Now, what's the opposite of a square root? I always think the mnemonic device is the opposite of a square root is the first word, which is to square it. So that's how I remember. If I had the cube root of a number, what's the opposite? Cube it. So I'm going to square both sides here. So 10 squared is 100. Root 2 times root 2 is 2. And over on this side, I'm left with 2x. If I'm going to solve for x, I'm going to divide by 2 and eliminate my 2's. Notice I didn't multiply those together because I saw that there was like a 2 over here. I could have had 100 times 2, which is 200, and then divide by 2, bringing us back to 100, but I just thought that that was a little easier. So x is 100. So that's how we can deal with radical equations. We get rid of these terms. Okay, now, so with number 3, we have a is to the 2/3, which is the same as the cube root of a squared. And that's it. That's all I have to do. You'll also notice that this is problem number 3. This is on the easier side, so my answer here would be D. Okay, so now we're going to get into dealing with radical equations and having potentially extraneous solutions. So extraneous solutions, you always have to look out for those. Always, always, always. So if you're taking notes on this, write down radical equations, always look for extraneous solutions, because with a radical equation, when you're squaring out both sides, you may wind up with two answers. We've got to test them back in and see if they work. So I'm going to go with number 5 first, and then I'll go to number 9. Okay, so here, k is greater than 0. They're just saying that your answer for k is going to be positive. They don't want a negative answer because all the answer choices are positive. And also x is 7, so we can substitute that in. So 2k squared plus 17 minus 7 equals 0. I'm going to move that 7 to the other side. So I get 2k squared plus 17 equals 7. And as we just did, the opposite of a square root is to square it. So we're going to square both sides, not just one side. Whatever you do to one side, you have to do to the other, which we did in the other problem, equals 49. And now I'm going to subtract 17 from both sides. So I'm going to move that over, and I get 32. And if I divide 32 by 2, I get 16, and the square root of 16 is 4. So k must be 4 for this problem. So whatever you do to one side, you're going to want to do to the other. Okay. All right, so now we have x minus a, and oh, by the way, a is 2, so I'm just going to straight away put that in there, x minus 2, equals x minus 4. Now here's the deal. This expression for number 5, you were squaring just a single number, but here you're going to square an expression, and you have to remember that when you square an expression, you have to write it twice and then FOIL. X squared plus 16 is not the same thing as multiplying that out twice and foiling that out. So I can picture the poster in our math hallway at school that's like, this is not the same thing as this. No, there's like a big no. So we have to remember to do that. And that's the fatal flaw for a lot of students. So I just want to point that out. I think I also pointed that out possibly with some of our functions with the algebra a couple weeks ago, but just in case I didn't, it's definitely something that we need to think about here with radical equations. Okay, so now I'm moving, what I'm doing here. I'm moving the terms to the other side. I'm setting them equal to 0. So I have x squared minus 9x plus 18, and then I go on to factor this expression. So x, and you can see the skills that we did in algebra are coming back again, and we have x is equal to 6, x is equal to 3. But the kicker is this. If I go back to my original expression before I start squaring anything, I need to determine if the terms work. Well, let's try with 6 first. 6 minus 2 is 4, and the square root of 4 is 2, and 6 minus 4 is 2, so 6 definitely works. That checks the box. If I take 3 minus 2, that would be the square root of 1, but 3 minus 4 is -1. They are not equal, so 3 does not work. So immediately when people get 3 and 6, they're like, A is my answer, that's it, and then they pick it. And that's where you can get this medium problem wrong because you didn't test for extraneous solutions. So your only answer is 6. So that's my big advice to you, test for extraneous solutions. Okay, so now we're going to move into exponent rules. So we're sort of toggling back and forth between these concepts of exponents and radical equations. Okay, so we have, okay, so we have xa squared all over xb squared equals x to the 16th. And they're saying that x is greater than 0. So we're dealing with all positive values here. And then they're telling you that a plus b is 2. We'll get to that in a second. My math teacher, props to Mrs. Rowe, way back when, always said, you know what? This fraction thing isn't really telling us division if it's written like that. So like rewrite it with the division symbol in between because that's a little easier to see. So thinking back to 1993 and remembering a math rule from way back when, is really useful because my brain, whenever I see a fraction sign, doesn't always register division. So I've always rewritten these problems in this manner. Now, division, when it comes to exponents, is to actually subtract your exponents. And because we have all the same bases, I can do that. So I can actually rewrite the problem this way. A squared minus b squared equals 16. Now, this is the difference of perfect squares. So I actually can factor this to a plus b times a minus b equals 16. Now, a plus b is 2 times some value equals 16. And the question's asking you, what's the value of a minus b? Well, a minus b must be 8. And you'll notice that I did not have to identify specifically what a and b were valued at. I just had to figure out the value of a minus b, which is 8, which would be the answer A. Okay, so looking at number 12, I have 9 to the 3/4. So that is going to be the cube root of 9 cubed. You can also break 9 down a little further if you wish, which I think is a little easier personally. So 9 is a result of 3 squared. So that would be 3 squared to the 3rd, which would be 2 times 3, or the 4th root of 3 to the 6th. So what we're left with is we can take a 3 to the 4th out, and then we're left with a 3 squared on the inside. So you'd have a 3 and then the 4th root of 3 squared. Well, if I were to just rewrite this part for a moment as that would be 3 to the 2/4, right? Which would be 3 times 3 to the 1/2. That would just have a final version of itself as the square root of 3, right? So it'd be 3 root 3, which would be D. So there are a lot of little interim steps that go into question number 12 and sort of breaking that down into its best available self. Okay, and then we have 11 and 13. So now we're getting into more advanced exponent rules here with these negative exponents, negative exponents. So with negative exponents, what you can do to make them positive is to put 1 over the number. So let's just start with a basic negative exponent. So if I have x to the negative 2, to make that positive, it's 1 over x squared. If I had 1 over x to the negative 2, to make that positive, you just put that in the opposite quadrant, and that would be x squared. Okay, so here, x to the negative 2, y to the 1/2, all over x to the 1/3, y to the negative 1. So let's work to make this positive. So what I would do is move your y to the negative 1 up and your x to the negative 2 down, because it has to go in its opposite quadrant to make it positive. So that means I'm going to rewrite this as y times the square root of y. Remember the exponents, right? They tell us that it's the square root or the cube root or the 4th root. And all the answers have square roots and 3rd roots anyway, so that's why I'm writing it that way. And then again, I'd have x squared and then the cube root of x. So my answer would be B. Okay. Number 13 here, a to the negative 1/2 equals x. What is a in terms of x? We want to get a all by itself. Well, we know that 1 over the square root of a, first of all, it makes it positive by 1 over equals x. And what's the opposite of a square root? Square it. And whatever we do to one side, we're going to do to the other. So that would be 1 over a equals x squared. And we want just a little old a by itself. So we're going to flip for the inverse, which means we flip over here, because whatever you do to one side, you have to do to the other. So it'd be a equals 1 over x squared. So there we are. So that takes us to the end of exponents and radical equations, and lots and lots and lots and lots of problems there. The next concept that we're going to roll into here will be proportional triangles and dealing with special right triangles and dealing with planes of triangles and opposite angles and all these sort of like smatterings of all these kinds of proportions, and maybe even a tiny bit of SOHCAHTOA as we get into that as our next concept. Okay, so here we go. So with number 18, they have these lovely triangles here, and they're telling us some information about these triangles. Okay, so I'm going to do my best drawing this because I know my like draw finder thing doesn't quite work this to draw triangles upside down, right side up. Okay, so here we go. C, D, B, A, E. Okay, ready? In the figure above, AE and CD are parallel to each other. Segment AD intersects CE at B. What is the length of C to E? All right, there's a very, very, very important hint that came up here. And that is the length of B to D and the length of B to A, because they're on the same length, but they're in proportion to each other. So here BD is 5 and the length of AB is 10. That means the length of BD is half of the length of AB. So I know that BE is 8, which means that CB must be half of that length, which is 4. And if I want the entire length of C to E, it would be 4 plus 8, which is 12. Okay. Okay, so then if we're taking a look at number 20 here, which by the way is the hardest problem in a section. So number 20 was the hardest problem in a section. So this is 23, this is 106, this is X. And as I mentioned earlier, the number of degrees inside of a triangle adds up to 180, and so does the straight line, which is going to be very important here. So if I look at my straight line, oof, that's really bad, sorry. Comical. So my straight line adds up to 180. 180 minus 106 leaves me with 9. Oh, wait, what am I saying? 74. Geez, my brain. Okay. So 180 minus 106 leaves us with 74. Okay, now here's what you can do. You can do 180 minus 74 minus 23, getting this angle, and then 180 minus that angle, getting you that angle. Or you can remember back to geometry that your exterior angle is equal to the sum of the interior two. So 74 plus 23 is 97, and that is your angle for X. Okay. I always feel like saying ta-da at the end of that because it's magic, right? The exterior angle is equal to the sum of the interior two. Okay. All right, so now we're going to deal with even more angles here. So I'm just going to draw the plane. I'm going to try to draw the triangles similarly here. And they're telling you with these hash marks that these are isosceles triangles, which means that these angles are equal to each other inside of that particular triangle, okay? And here you have Y, and here you have Z. Come on, Z. Z. And here you have X. Okay, and we know some information about this. We know 180 minus Z equals 2Y. And we also know that Y is 75, and 2 times 75 is 150. So 180 minus Z equals 150. So that must mean that Z is 30. Okay, so Z is 30. And if I'm left with 150 and I cut that in half, I know that these are each 75, right? These angles here are 75. And if I also know that I have a straight line that adds up to 180, I could just do 180 minus 75, which leaves me with the angle measure for X, which is 105. Ta-da! So there we go. Okay. So more with proportional triangles and side lengths. Okay. So here we have a triangle, ABC, that is a right triangle. This looks like D. Okay, ABC. Okay. And we know that AC is 20 and BC is 16. Uh-oh, I didn't quite draw that to scale, my fault. Okay. And honestly, if you did Pythagorean theorem, you would find out that this is 12. So that should be a little bit of a smaller side than my BC, but that's okay. If you also recognized that this is a 3, 4, 5 triangle. So they love to mess with that on these proportional triangles. So 3, 4, 5, because if you break that down, if you divide 12 by 4, it's 3, 16 by 4, it's 4, 20 by 4, it's 5, 3, 4, 5. Okay, now we have a secondary triangle, which is called DEF, and it's 1/3 of the length, which, by the way, I'm not going to find 20 over 3 and 16 over 3. Like, it doesn't matter the actual side lengths. They want to know what is the value of the sine of f. So here we're using proportional triangles in a different way. We're going to use SOHCAHTOA. So I mentioned that earlier. We're going to get to more of it in the next slide as well. But sine is opposite over hypotenuse. Well, if these are similar triangles, taking the sine of f is the same thing as taking the sine of c. And if you don't know that it's a 3, 4, 5 triangle, and you're just dealing with what is, 12 over 20 reduces to 6 over 10, which reduces to 3 over 5. So that is going to be your sine of f. So you can see they bring up proportional triangles in lots of different ways. Okay, number 16 is a proportion where they're slicing this proportion straight up and down. So here we have a triangle with smaller triangles drawn inside of it. So we have this little shelf, and then we have like the big cutout for the shampoo, and then we have this bottom shelf. And the total height up and down is 18. And the proportions are listed on the side, 2x, 3x, and x, which throws everybody off, by the way. They think, oh, well, that is only applicable to the side length. No, if you cut something up, down, sideways, and it's all part of the same shape, that proportion is also going to reference if you were to cut it straight up and down. So if I have 2x plus 3x plus x equals 18, so 6x equals 18, x is equal to 3, and what's the height of the shampoo shelf? 3 times 3 is 9. So no matter how you slice it, whether it's on its side or straight up and down, those proportions are going to remain intact. And here's just one other words of proportion, like the first one that we rolled through. I have a couple more slides, and I don't want to go over a crazy amount of time into I want to give you as much as possible here. So I'm going to talk quickly about SOHCAHTOA. We'll get into and then I want to spend some time on imaginary numbers, unit circle, and advanced shapes. Okay, so I reminded everybody earlier about SOHCAHTOA, and I just want to go over like a quick review of what that looks like. And I'm just going to use a quick 3, 4, 5 triangle to do so. So 3, 4, 5, here's your right angle. So SOHCAHTOA. Okay, so I'm going to call the side lengths A, B, and C. So you'll notice that the sine of A is opposite over hypotenuse. The cosine of A is adjacent over hypotenuse. And the tangent of A is opposite over adjacent. And then we flip. Now I'm going to start with C. So the sine of C is opposite over hypotenuse. Cosine of C is adjacent over hypotenuse, and the tangent of C is opposite over adjacent. And you'll notice that the sine of one is the cosine of the other, and the cosine of one is the sine of the other, and the tangents are the inverse of each other. And this is really important to note, because let's talk about this as x here. So they say the sine of x is 4 over 5, which is true based on my shape. So what's the cosine of this fancy thing called 90 minus x? Well, 90 minus x is simply the angle measure that is split between these two angles, not the hypotenuse angle, because you're never taking the sine, cosine, or tangent of the hypotenuse angle. It's simply of what is left. So if it's cosine of 90 minus x, you're referencing the other angle. Let's call that y. So if I want the cosine of y, that's going to be adjacent over hypotenuse, which lo and behold is the same thing as the sine of x. So it's just the same thing as saying, I'm going to take the cosine of y of the other angle. So it's just a confusing way of referencing that. Likewise, if they separate the angles here, like they did for A and B for number 23, those are two angles coming from the same triangle. Those angles have to add up to 90. There's no other way around it. So you can say 4k minus 22 plus 6k minus 13 must equal 90 because those are the two angles that are being pulled apart from that triangle. So then you can say 10k minus 35 equals 90, 10k equals 125, which means k must equal 12.5. So they love to use SOHCAHTOA in a funky way, okay? All right, moving into imaginary numbers. And one thing that the SAT does that drives me absolutely batty is that it tells you that I is equal to the square root of -1, and that everybody goes around plugging in the square root of -1 in for I, and you'll look at all of the answers and they still have I in it. That's not the rule that's important with imaginary numbers. I squared is equal to -1, replacing any I squareds that you find with -1, that is important. But the square root of -1 equaling I is not. Okay, so 3 minus 5I all over 8 plus 2I. So to get rid of I in the denominator, you're going to multiply by what we call as the conjugate. It's the opposite sign assigned between the first and second terms in both the numerator and the denominator. So we're going to go into our FOIL, and doing so, we're going to treat I just like an X or a Y here. We're not going to replace it yet. So let's just treat it as an X. So 3 times 8 is 24. 3 times -2I is -6I. -5I times 8 is -40I. -5I times -2I is positive 10I squared. Okay. All over 8 times 8, which is 64, minus 16I plus 16I minus 4I squared. You'll see that because I multiplied this by opposite signs, it rationalized the i's out of the denominator, and I'm simply left to replace I squareds with -1. So this is going to be -1, and this is going to be -1. Okay, so 24 minus 10 is 14. -6 and -40 would be -46I. And then here, 64 plus 4 is going to be 68. And I can reduce everything by dividing by 2, so it'd be 7 minus 23I all over 34. So that would be my answer. So multiplying by the conjugate, but also only replacing I when you're dealing with I squared is going to be really, really helpful here. You can see that this is another problem of the same type. So I'll ask you to try that on your own so you can take a look at that and see if it works for you. Number 4 is actually a pretty simple problem. It was an early problem in one of the sections. But what everybody messes up with for number 4 is the distribution of that negative that's sitting outside that 9I squared. So you'd have 5 plus 12I minus 9I squared plus 6I. Notice all the answers still have their i's intact. So I'm going to replace this with -1. So I have 5 plus 9, which is 14, plus 18I. So pretty straightforward once we know how to distribute. Okay. Okay, this takes us to our buddy unit circle. So what I'm going to do is actually make this quite small so we can see the two problems that are here. And then I'm going to bring up a circle over here, and I'm going to describe unit circle in the most plain terms possible. So if you're algebra 1, algebra 2, geometry, it really doesn't matter. If you're functional math, you know, any of those things, I want you to be able to understand it. Also, that's pretty good. It's pretty close to being on an axis. What I'm going to do is also just draw a straight line up and down here, even though it's not perfect, but it'll be close enough for our purposes to cut this into 4 equal-ish quadrants. Okay, cool. All right, so this is quadrant 1. Oops, I'm still drawing a shape. Quadrant 1, quadrant 2, quadrant 3. That is a really bizarre 3. Quadrant 3, and quadrant 4. You'll notice that I went counterclockwise. That's what happens with the unit circle. It goes counterclockwise. If you're in calculus, or pre-calc, and you've learned unit circle, you may have learned the mnemonic. All students take calculus. At some point, you take some form of it, whether it's the course or not. So, and that's a mnemonic for how we address SOHCAHTOA in a unit circle. So let me just add in the degrees here, and I'm going to add in the radians. Radians are based on radius, which is a portion of circumference, and we did that earlier with our length of an arc and area of a sector. So if I go all the way around, I've gone 360 degrees. Known fact, there are 2 pi radians in a unit circle because it's based on a radius of 1, and when we think of circumference, 2 pi r, 2 pi times 1 is 2 pi. So that's where this 2 pi is coming from. If I go halfway around the circle, the circumference is just pi. If I go a quarter of the way, it's pi over 2. If I go 3/4 of the way, it's 3/2 pi. Okay, so these are some of our basic pieces. It's not necessarily going to come up on the SAT that we need to know sine, cosine, and tangent inside of a unit circle. But I will say this, that if you know this and you take the ACT, it's really useful. In quadrant 1, all sine, cosine, and tangent are positive, and everything else that's going to be positive will be listed uniquely in each of my little mnemonics here. So you can imagine sine is positive in quadrant 2, which means what is not listed, cosine and tangent, are negative. Tangent is positive in quadrant 3, which means what's not listed is negative, cosine and sine. Cosine is positive, but sine and tangent are negative. Now, we don't need that for the SAT. I'm just telling you that because that's important stuff if you're going to take the ACT. Here, we actually just need to know the basics, which was that conversion from degrees to radians that I did earlier. So it'd be a degree out of 180 reduces to pi over some number. Okay, so let's pretend our angle is 30 degrees again. We did this earlier with the 30, 60, 90 triangle. So that would be 30 out of 180 reduces to 1/6, which is reduced to pi over some number, 6. I like that interim reduction. I think it's helpful just to be able to see it. Let's try this with a 45, 45, 90 triangle. Technically, it would be written as a triangle here inside of the unit circle. So 45 out of 180 is reduced to 1/4, which is known as pi over 4. So that's where all of these are coming from. 180 out of 180 is 1, so it's just 1 pi. 270 out of 180 reduces to 3/2 or 3/2 pi. So like that's where this unit conversion is coming from. Okay, so let's turn our attention to number 34. In a circle with center at O, and it has an angle AOB, has a measure of 5/4 radians. Okay, so essentially like you have a circle and you have this length of the arc, and that's known as 5/4 pi. Oh, by the way, that's like 1 1/4 pi. That angle would be like way over here. Let's be real. So really that would look like that. Okay, so it'd be 5/4 pi. And they want to know what's the fraction of the whole area of the circle. Well, the whole area or radians of the circle is 2 pi. So 5/4 pi out of 2 pi is the same thing as 5/4 pi times 1/2. So that would just be 5/8 of the whole circle. So that's what that looks like. So sometimes they have these problems where it looks really complicated, where I gave you way more information than what you need, but some of the basics of converting from degrees to radians, and you didn't need all of that. Number 18, the number of radians in a 720-degree angle could be written as a pi. All right, well, we know 360 is to 2 pi, as 720, that's 360, is to 2 pi, is to what pi? Well, isn't this double 360? So that would be 4 pi. So A would be 4. So they can take a concept of unit circle, which is quite confusing and really sort of scary looking, and make it, it's actually not as bad as we thought. Okay, so this is our last slide, and this is where we're putting a number of concepts together to be able to address lengths of sides and area of pieces here. Number 30 is the most complex thing I will do. I'm actually going to start with some of the easier problems on the right. I should have reversed it. I don't know why I didn't do that. So I'm going to start with the easier problems here, talking about 30, 60, 90, 45, 45, 90, and then working our way over to the other side. So here we have a triangle, which they're telling us it's 30, and then this angle is 60, and then this is 90, which means that this is also 30, and this length is 12, which means if you know the properties of a 30, 60, 90, this bottom leg is half of the hypotenuse, which is 6, and then the height would be 6 root 3. And they're saying, okay, hey, what's the length of A to D? Well, that's got to be the same as this side, has to be 6, because they have to add up to 12, because we know that an equilateral triangle, when you cut it in half, makes for a 30, 60, 90. This is going to be an important point when we look at this more complex shape that we're going to break down in a couple problems here. Okay, so here's a circle-ish. So here's a circle, and I'm just going to draw this like funky looking set of like triangle stuff inside of it. Okay, and these angles are 20, and this angle is 20, and they want to know what that angle is. All right, so here's the thing. You can break this into smaller triangles. I can break this into isosceles triangle. So if this is 20, then this guy's 20, then that means this guy's 140. Well, that would be the same thing over here. So this would be 140. And so if I were to go all the way around, I form a circle. So 360 minus the sum of those two, which would be 280, leaves me with the angle measure here, which is 80. There's also something called the reflexive angle property. So if I know that these two are 20, which adds up to 40, on that exterior, that angle that's over here, this interior angle will be double that number. And if I were to reflect it out and say that this is 40, right, then that also would turn out to be 80. So it's kind of like a fun property. More geometry, right? So this is where they're going to use, and look at this, I found very few problems where we're talking about like cones and rectangular solids and cylinders. This is one of the only ones I can find in practice tests 1 through 8. You'll notice that they have a cone up top, a cylinder in the middle, and a cone at the bottom. So we need 1/3 pi r squared h, 2 of those, plus pi r squared h for the cone in the middle. I'm sorry, the cylinder in the middle. So they want the total volume of the silo. So grain silo is built to form 2 right circular cones and a right circular cylinder with internal measurements represented in the figure above. Which of the following is the volume? Most people will forget that there's 2 cones total, and they'll only give me 1, and we'll get a different answer than what is the answer here. And of course they list it. So that's really annoying of College Board, but that's how they try to trick you, right? And so we are not going to be tricked. And so here, I'm just plugging in the values for radius and height for each of these things. Okay, so what I'm gonna do is calculate this out. So 5 squared is 25, 25 times 5 is 125, 125 times 1/3 is 41 2/3 times 2 is 83 1/3 times pi is 261.8. Okay. And then 5 squared is 25, and 25 times 10 is 250, and 250 times pi is 785.4. And we add those together, 261.8, you get 1047.2. Now, indulge me for a second. If I added only half of this, I get C. And a lot of people pick the answer of C, and that's where they run into trouble. Okay, last problem. I'm going to slow down a moment because I've been speaking quickly here. And this is the hardest problem that we will do together, other than completing the square that we did earlier, where we had to divide everything by 2 and deal with decimals. That's a pretty yucky one too. Oh, that is a gem of a drawing, everybody. I'm sure if you have little siblings and they can color, they can probably color and draw better than that lovely hexagon that's there, but best I can do today. Okay, so here the figure above shows a regular hexagon. Remember we talked about regular shapes? That means all the sides are equal. And it says with side lengths of A. So you'll see, because it's regular, I labeled everything A. And then you have a square with side lengths of A. So you'll notice that has side lengths of A. Okay, so that means I can break this hexagon down into equal parts, equal angles, essentially, if I wanted to. And they say the area of the hexagon is 384√3. So if I took this hexagon and I broke it into 6 equilateral triangles, that's going to help me. Okay. And it says, what is the area of the square? Well, area of the square is that I'm eventually trying to find what A squared equals. So let me take 384√3, and I'm just going to divide it by 6. I'm going to leave the √3. I'm not going to make that all fussy. So I get 64√3. Okay. Let's take one equilateral triangle. And I made a fuss about this just a moment ago. You have equal sides, equal angles, right? All the angles are 60. Okay. And I know the area of this. Now, by the way, if I cut this in half, I get 2 30, 60, 90s, which we spoke about as well. See how all this comes together? Let's talk area formula of a triangle. It's 1/2 base height. These are one of the known formulas they give us. And that equals 64√3. Our base is known as A, right? Because the base is A. So that'd be 1/2 of A. But finding the height is going to be a little more difficult. Okay, so this is A. If this is A divided by 2 because it's half of it. And this is A√3 divided by 2 because we're doing the properties of a 30, 60, 90. So A√3 over 2 is that height, equals 64√3. Okay, so I get A squared √3 over 4 equals 64√3. And then 64 times 4 is 256. So A squared √3 equals 256√3. And let's get rid of the √3s. I'm left with A squared, which is what I'm trying to find, which is 256. So my answer would be A. But you'll notice that taking these larger shapes and breaking them down into either like 30, 60, 90, 45, 45, 90 special right triangles can be really helpful when they're trying to present something that's really confusing to you. So a larger shape is made up of smaller shapes. So always know that. So that takes us to the end of math. So that offers us a little opportunity here to have any sort of questions. If you'd like me to answer any specific math questions, if you've been practicing any math, if there's anything that you'd like me to show you now, I'm also happy to set up time again if you'd like me to go through particular problems as you start to practice tests and you'd like me to go over it with you and give you additional problem sets. I'm happy to do that. But I'd just like to thank you all for your time. It's been awesome just connecting with people in a different place and honestly keeping me keeping me thinking about math. And
it's been so great. This has been so great for everybody. And I'm just so grateful for you for doing this. And I think that it's going to make a big difference. So,
great.
yeah.
Well, anytime you need anything math, reading, grammar, science oriented, if you'd like me to take anyone through basics of how to approach an ACT exam, if that comes down the path for anyone, I'm happy to do that as well.
That is so nice of you. I'll probably be back in touch.
Well, thank you,
so
Marissa,
much.
Samantha, Abby, Brian, Ethan, and Kennedy, and Denny. It's been a pleasure, everybody. And I wish you the best of luck on the rest of your school year and future testing. And
Yeah.
I'm happy to help.